begin in silence. The universe unfolds not as a void, but as a vast, invisible sea. Its surface is space-time, the great fabric upon which galaxies drift like distant islands, while gravity bends and folds it like currents beneath the waves. To human eyes, this fabric seems like emptiness, a dark stillness stretched between the stars. But physics whispers another truth, that beneath this apparent calm lies a restless ocean, a hidden depth upon which existence itself floats. Einstein once revealed that space-time is no longer a passive stage, but an actor, pliable and alive, warping under the weight of stars and collapsing under the fury of black holes. Yet modern physics points beyond even this revelation. It suggests that space-time itself is not the final layer of reality, that beneath its flowing geometry lies a deeper substrata, forgotten ocean that surges unseen. This is the quantum vacuum, a sea of fields that never sleep, fluctuating with ghostly particles that blink into being and vanish in an instant. A vacuum that is not empty, but charged with invisible energy, a storm in silence. Here lies the paradox. If space-time is the surface, then what is the sea below? Is it the zero-point energy from which particles are born? The primordial field, that ignited cosmic inflation, or something stranger still, a realm where reality itself dissolves into information, where time and distance lose all meaning? Every particle collision, every measurement of cosmic expansion, points toward the same haunting possibility. Space-time may not be the foundation, but only the foam upon a greater sea. The story begins with Einstein's equations, but ends with a mystery, a hidden ocean beneath creation itself. For most of human history, the cosmos appeared as an empty backdrop, a dome of night, silent and still, upon which the stars were painted. Civilizations gazed upward and saw permanence. The stars were eternal fires, fixed in place. Between them, nothingness stretched in absence so profound that even thought seemed unable to penetrate it. In ancient Greece, Aristotle resisted the very notion of emptiness. To him, the universe abhorred the void. Every place was filled with substance, with purpose, with matter. The cosmos was not an ocean, but a clockwork, and it could not tolerate gaps between its gears. The void was dismissed not just as impossible, but as unthinkable. Yet the question never vanished. Centuries later, it surfaced again in a different form. In the 17th century, Isaac Newton reshaped the world with laws of motion and universal gravitation. For Newton, space was not alive. It was not a fabric nor a field. It was absolute and infinite, immutable stage upon which the actors of matter played their parts. Stars, planets, and comets moved as dancers across an unchanging floor. The emptiness between them was pure void, an infinite container, indifferent to what it held. And yet, Newton's framework carried within it a quiet seed of paradox. If space was infinite and absolute, how could it be influenced by the matter it contained? Was the void truly nothing, or was it something deeper, unseen? At the time, such questions were left unanswered. The void remained a silent background, a mathematical canvas stretched across eternity. 2 centuries later, Albert Einstein shattered that silence. With his theory of general relativity, published in 1915, space-time was revealed not as a stage, but as an actor itself. The void had structure. It could bend, curve, and ripple. The presence of stars and galaxies did not merely move within space, they shaped it. Gravity was no longer a force in the Newtonian sense, but the bending of spacetime's fabric, as though the universe were a vast ocean, its currents stirred by the weight of suns. This revelation marked the first true glimpse of the forgotten ocean beneath spacetime. What had been thought of as empty was now alive, flexible, dynamic. The surface of reality was no longer silent. It could flow, it could twist, it could collapse into the abyss of a black hole, or stretch across cosmic scales to carry galaxies apart. Yet even Einstein's ocean had its limits. Beneath relativity, quantum mechanics was already rising, carrying with it a new vision of emptiness. In the early 20th century, Werner Heisenberg articulated a principle that would forever change the meaning of nothingness. His uncertainty principle revealed that, even in the absence of matter, the vacuum could not be still. Position and momentum could never both vanish into precision. Even the emptiest space must tremble with fluctuations. Soon after, Paul Dirac added another layer of depth. His equations describing the behavior of electrons hinted at a strange consequence, a sea of negative energy states filling what had once been called empty space. This Dirac sea became an early metaphor for the forgotten oceana, hidden reservoir, invisible yet essential, whose fluctuations gave rise to the very structure of particles. Still, these were theories, shadows on chalkboards. It would take experiment to prove that the vacuum itself was alive. That proof came in the mid-20th century. In 1947, physicists Willis Lamb and Robert Rutherford observed a subtle shift in the energy levels of hydrogen atoms. This Lamb shift could not be explained by classical theory. It was evidence that even in the supposed emptiness around an electron, invisible fluctuations were at work, nudging its orbit ever so slightly. The vacuum was no longer hypothetical. It left measurable fingerprints on the atom itself. A year later, in 1948, Hendrik Casimir revealed another strange consequence. Two metal plates placed close together in a vacuum would experience an attractive force, as though the emptiness itself were pressing them together. This became known as the Casimir effect. What appeared as void was in truth a restless ocean of fluctuating fields, exerting pressure even when no particles were present. For the first time in history, humanity had touched the forgotten ocean, not metaphorically, but physically. Instruments in the laboratory confirmed what theory had whispered: emptiness is not empty. Meanwhile, another discovery pushed this ocean onto cosmic scales. In 1965, Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, detected a faint hiss of microwave radiation. At first, they thought it was interference perhaps from pigeon droppings on the antenna, but the signal would not vanish. It was isotropic uniform across the entire sky. This was no noise. It was the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation was more than a relic. It was evidence that the newborn universe had once been a storm of particles and fields, dense and hot, where quantum fluctuations were amplified to cosmic proportions. It was as though the forgotten ocean had erupted, driving the birth of spacetime itself. In the early 1980s, Alan Guth and Andre Linde developed the theory of cosmic inflation. According to this model, a primordial fielder kind of vacuum energy drove an exponential expansion of the universe in its first fraction of a second. This inflationary sea smoothed the cosmos, stretched quantum ripples into the seeds of galaxies, and left imprints visible today in the cosmic microwave background. The forgotten ocean was no longer confined to atomic scales. It had become the engine of creation, shaping the cosmos on the grandest stage. Key figures stand like lighthouses across this unfolding discovery. Newton, who saw emptiness as absolute stage. Einstein, who transformed it into a curved, living geometry. Heisenberg and Dirac, who revealed its trembling uncertainty. Lamb and Casimir, who proved its pressure in the laboratory. Penzias and Wilson, who heard its relic glow from the dawn of time. Guth and Lind, who imagined it as the storm that birthed the cosmos itself. Each step brought humanity closer to a profound recognition that the vacuum is not absence, but presence, not silence, but a hidden orchestra of fields and forces. By the close of the 20th century, the forgotten ocean beneath spacetime was no longer a poetic metaphor. It was physics itself. Every atom, every star, every galaxy was built upon its restless tides. Every experiment with light and matter carried echoes of its fluctuations, and every attempt to describe the cosmos pointed back to its unseen depths. Yet mystery lingered. For if the vacuum is filled with energy, how much energy does it hold? Quantum field theory predicted an answer so vast it defied comprehension. A vacuum energy density 120 orders of magnitude greater than what cosmology observes. This was the first whisper of the cosmological constant problem, the most severe mismatch between theory and observation in the history of science. The forgotten ocean was not merely deep. It was paradoxical. It behaved as though its tides were almost perfectly balanced, cancelling themselves out across creation, yet leaving just enough residue to shape the universe. The discovery phase had begun with simple questions about the void, and ended with a revelation that nothingness itself might be the most fundamental something. Humanity had uncovered the surface of a sea that stretched beneath all of reality. But what lay beneath that surface remained unknown. The stage was set for shock. The discoveries of the 20th century did more than reveal hidden depths. They shattered the very notion of what emptiness could mean. What had once been dismissed as nothingness was revealed as an ocean of fields, restless with unseen energy. And from this revelation came the greatest shock in modern physics, that the very equations of nature may be catastrophically wrong when they attempt to measure the void. The first tremor of this realization came from quantum field theory. In its equations, the vacuum was never silent. Every quantum field, the electromagnetic field, the electron field, the quark and gluon fields, possessed a zero-point energy, a kind of irreducible hum that could not be eliminated. To calculate the energy of empty space was to sum over all these fluctuations across all possible frequencies. The result was staggering. A prediction that the vacuum's energy density was virtually infinite. Of course, infinities are the mathematician's alarm bells, the warning that something in the description has slipped beyond control. Physicists employed renormalization techniques to tame these divergences, subtracting infinities from infinities until finite results emerged for measurable quantities. For the behavior of particles and atoms, this strategy worked astonishingly well. Quantum electrodynamics, the theory of light and matter, produced predictions accurate to more than 10 decimal places. Yet, when the same machinery was applied to cosmology, the outcome was grotesque. The theoretical vacuum energy density was not just large, it was larger than what observations allowed by a factor of 10 to the power of 120, one followed by 120 zeros. A mismatch so extreme it dwarfed every other discrepancy in physics. This was the cosmological constant problem, the deepest failure of theory against experiment ever encountered. If the forgotten ocean truly contained such energy, the universe would have torn itself apart in an instant. Galaxies, stars, and atoms would never have formed. Reality, as known, could not exist. And yet, here it was. This was the first great shock, the realization that the equations describing the vacuum predict a universe utterly unlike the one humanity inhabits. The void was no gentle background. It was a paradox threatening to unravel the coherence of physics itself. The second shock emerged not from mathematics, but from the cosmos itself. In the late 1990s, two independent teams of astronomers studying distant supernova expected to confirm a slowing expansion of the universe. Gravity, they believed, should be tugging on cosmic scales, decelerating the outward rush of galaxies. Instead, the data showed the opposite. The universe was not slowing down, it was accelerating. This discovery stunned the scientific world. Some unseen force was driving galaxies apart, stretching space-time faster and faster with every passing epoch. The culprit was named dark energy, a phrase that concealed ignorance with poetry. But behind the term lurked the same ancient ocean. For what is dark energy, if not the energy of the vacuum itself, seeping into Einstein's equations as a cosmological constant? Einstein had once introduced that constant reluctantly, a mathematical trick to preserve a static cosmos. When expansion was later discovered, he discarded it, calling it his greatest blunder. But now, decades after his death, the constant had returned with a vengeance. The universe itself demanded it. The forgotten ocean was not only real, it was expanding the cosmos, reshaping destiny on the grandest scales. This was the second great shock. The void, far from being empty, was revealed as the dominant force of the universe. More than 2/3 of all cosmic energy is hidden within it. Galaxies, stars, planets, and life, everything visible are but small ripples compared to the unseen depths. The forgotten ocean had risen to rule the cosmos. The third shock came from the confrontation between relativity and quantum theory at the edges of space-time. In Einstein's smooth geometry, black holes were inevitable, regions where matter collapses so completely that nothing, not even light, can escape. At their centers lurked singularities, points of infinite density where the equations of relativity broke down. For decades, physicists believed these infinities were mathematical curiosities, artifacts of idealized models. But then came the work of Roger Penrose and Stephen Hawking in the 1960s and 70s. Their singularity theorems proved that under broad and realistic conditions, such singularities were not avoidable. They were not artifacts. They were inevitable. If general relativity is correct, space-time itself collapses into points where curvature becomes infinite, where time ends. Here again, the equations betrayed themselves. Just as in quantum field theory, infinities erupted. The ocean beneath space-time refused to be described. And if black holes were real-ass observations of X-ray binaries and galactic centers confirmed, then these singularities were not abstractions. They were real features of the universe, places where the forgotten ocean erupted into paradox. But Hawking went further. In the mid-1970s, he combined relativity with quantum mechanics and discovered that black holes are not eternal. Quantum fluctuations near the event horizon can create pairs of particles, one falling inward, the other escaping outward. To an outside observer, the black hole appears to radiate. Over time, it evaporates, vanishing into the ocean of quantum fields. This prediction Hawking radiation was a revelation. Black holes, the very symbols of inescapable gravity, could dissolve into nothing. The forgotten ocean was not passive. It created particles from the void itself, and with this creation came the most disturbing paradox of all, the information problem. If a black hole evaporates completely, what happens to the information about the matter it once contained? Quantum mechanics insists that information cannot be destroyed, yet relativity suggested it could vanish into the abyss. Here, at the horizon of black holes, the two great frameworks of physics collided head-on. The ocean beneath space-time became a battlefield where quantum theory and relativity tore at each other, each refusing to yield. This was the third great shock, that the void, when probed deeply, does not yield a coherent description. The equations of science contradict one another. The ocean beneath space-time conceals truths that the current language of physics cannot reach. And so the story of discovery turned into one of crisis. The vacuum was not absence, but presence, not silence, but storm. It gave rise to forces that pushed metal plates together, shifted electron orbits, and filled the sky with relic radiation. It drove the expansion of the universe, accelerated its future, and perhaps even seeded its birth. It created particles at black hole horizons, while threatening to erase information itself. Each revelation brought awe, but also terror. For what does it mean if the foundations of physics collapse at the very place they should be most secure? What if the void, instead of being a foundation, is itself a mirage, an emergent surface concealing a deeper order still? By the dawn of the 21st century, physicists stood in a state of uneasy wonder. Their equations had led them to the ocean, but also betrayed them with paradoxes. Dark energy ruled the universe, yet no theory could explain its value. Black holes radiated, yet no framework could resolve the information they devoured. The vacuum was not empty, but enlivened in its depths. Mathematics itself faltered. The forgotten ocean was no longer metaphor. It was the greatest enigma of modern science. The shocks of discovery left physics trembling. Emptiness was no longer nothing. It was a restless sea, surging with paradoxes. But science does not turn away from turbulence. It dives deeper. If the forgotten ocean beneath space-time exists, then it must leave ripples, currents, and tides that can be measured. And so, the great machines of the modern age were built, each one designed as a probe into the invisible waters beneath creation. The first and most direct probes were particle colliders. Within them, beams of protons are whipped to near-light speed, then slammed together in bursts of energy mirroring the conditions of the infant cosmos. At CERN's Large Hadron Collider, buried beneath the border of Switzerland and France, detectors as large as cathedrals recorded the debris of such collisions. In 2012, from trillions of events, a pattern emerged: the Higgs boson. This particle, long predicted but unseen, revealed the existence of the Higgs field, an invisible ocean permeating space-time, endowing particles with mass. Without this field, quarks and electrons would drift weightless, unable to form atoms or molecules. The universe, as known, would not exist. The forgotten ocean was no longer an abstraction. It had been touched, if only briefly, by human machines. Yet even this triumph carried unease. The measured properties of the Higgs suggested a troubling possibility that the vacuum of our universe may not be stable. The Higgs potentialer, mathematical curve describing its energy states, hinted that our cosmos rests not at the lowest valley, but upon a plateau. If true, then the vacuum is metastable, like a calm sea hiding a deeper trench. One quantum fluctuation, one shift in conditions, could trigger a catastrophic collapse to a lower state, rewriting the very laws of physics in an expanding bubble of destruction. This possibility, known as vacuum decay, remains speculative, but it darkens the horizon of scientific imagination. While colliders probe the ocean structure at the smallest scales, the cosmos itself offers the largest experiments. In the 20th century, satellites like COBE, WMAP, and later Planck mapped the faint afterglow of the Big Bang, the cosmic microwave background. What they saw was more than static. It was a subtle pattern. Tiny fluctuations in temperature, no more than 1 part in 100,000. These ripples were fossils of quantum fluctuations, stretched across the universe during its first fraction of a second. Here was direct evidence that the forgotten ocean beneath space-time was not silent. Its fluctuations, amplified by cosmic inflation, became the seeds of galaxies, the scaffolding of stars and planets, the framework of existence. Every galaxy, every world, every living being owes its origin to those ripples in the vacuum. The ocean beneath space-time shaped the cosmos on the grandest scales, but deeper investigation demanded precision. The Lamb shift in hydrogen atoms had shown that vacuum fluctuations alter electron energy levels. The Casimir effect revealed their pressure between metal plates. Now, laboratories refined these experiments, measuring with exquisite sensitivity. With mirrors and superconducting circuits, physicists coaxed the vacuum into revealing its strength. They found that by controlling geometry, materials, and boundaries, one could manipulate the push and pull of the void. The forgotten ocean could be engineered, if only in whispers. Quantum electrodynamics, the theory governing these interactions, had already been tested to extraordinary precision. The anomalous magnetic moment of the electron-matched experiment, to 10 decimal places. No other theory in science had ever achieved such accuracy. And yet, when its predictions were turned to cosmology, the numbers broke into absurdity. The forgotten ocean appeared calculable in detail, but unknowable in essence. Meanwhile, new eyes opened upon the universe. In 2015, the LIGO observatories detected gravitational waves, ripples in space-time itself, born from colliding black holes more than 1 billion light-years away. At last, Einstein's prediction had been confirmed. Space-time was not rigid, but fluid. It could carry waves, just as the sea carries swells. And where there are waves, there is medium. Perhaps these ripples were not moving through emptiness, but across the unseen ocean beneath. Some physicists dreamed further. If primordial gravitational waves could be detected, they might carry messages from the first instant after the Big Bang, before even light existed. Unlike photons, which scatter, gravitational waves can pass through matter unimpeded. They could pierce the veil, carrying echoes from the deepest currents of the forgotten ocean. Future detectors, like the space-based LISA mission or vast pulsar timing arrays, may someday capture these signals. If found, they would open a new window upon the origins of everything. In laboratories, other frontiers emerged. Cold atom experiments created analog black holes, trapping sound in fluids the way gravity traps light. From these artificial horizons, faint radiation leaked Hawking-like in character, born from vacuum fluctuations. These tabletop oceans whispered the same truths as the cosmos. The vacuum is creative, restless, alive. Supercomputers joined the exploration, simulating quantum chromodynamics, the theory of quarks and gluons, across vast computational lattice. They revealed how the vacuum seethes with gluon fields, binding quarks into protons and neutrons. Without this hidden storm, matter itself would dissolve. Here again, the forgotten ocean was no backdrop. It was the architect of permanence, and yet every layer of discovery deepened the mystery. The Higgs field explained mass, but not stability. The cosmic microwave background revealed fluctuations, but not their origin. Gravitational waves confirmed relativity, but not its union with quantum theory. The Casimir effect measured vacuum pressure, but not its cosmological scale. Every answer fractured into more questions. Even the question of time itself became suspect. If space-time is not fundamental, but emergent from deeper quantum structures, then what does it mean for time to flow? Is time an illusion, a pattern, rising from entanglement in the ocean's depths? And if so, is the past truly gone or merely hidden? By the dawn of the present century, humanity's instruments had revealed a universe where emptiness was crowded with fields, where silence was filled with fluctuations, where the fabric of reality itself seemed provisional. The forgotten ocean. Beneath space-time was everywhere, in the smallest shifts of electrons, in the largest patterns of galaxies, in the whispers of black holes, in the acceleration of the cosmos. But with each new discovery came a humbling recognition. The ocean revealed itself only in fragments. A ripple here, a fluctuation there, a distant horizon shimmering with paradox. Never the whole, never the depth entire dot. And so science pressed onward, deeper still, knowing that beyond every breakthrough waited another abyss. The deeper science waded into the forgotten ocean, the more turbulent its waters became. What once seemed a triumphant ability to measure vacuum fluctuations, to discover the Higgs field, to map the primordial ripples in the cosmic microwave, background soon revealed itself as a prelude to something far stranger. The greatest puzzle emerged from the universe's expansion. In 1998, astronomers observing distant supernova expected to find that gravity had slowed cosmic growth. Instead, they found acceleration. Galaxies were not only drifting apart, they were speeding away, as if pushed by an invisible hand. To explain this, physicists revived an idea Einstein himself once abandoned: the cosmological constant, energy, embedded in empty space itself. Dark energy. Here, the forgotten ocean surged into the heart of cosmology. If vacuum energy drives cosmic acceleration, then the void is not only alive, but dominant. Nearly 70% of the universe appears to be this dark energy, invisible and untouchable, yet dictating the fate of all things. Stars, galaxies, clusters mere foam on an endless sea. But when quantum field theory is asked to calculate the vacuum's energy, the results defy reason. The predicted value is larger than observation by 120 orders of magnitude, the greatest mismatch between theory and measurement in the history of science. It is as though physics had peered into the ocean only to find it bottomless. Why is the energy of the vacuum so small, yet so decisive? Why does the ocean beneath space-time whisper when theory insists it should roar? The mystery deepened further with black holes. At their horizons, the interplay of quantum fields and curved space-time produces Hawking radiation particles emerging from nothing, as if the ocean were boiling at the edges of gravity's abyss. But this process unleashed another paradox. The information problem. If black holes evaporate, what becomes of the information they contain? Does the ocean beneath space-time allow erasure, violating quantum law? Or does it conceal information in ways still unknown, perhaps on the horizon itself, encoded in patterns too fine for present science to read? This tension between quantum mechanics and relativity, the two pillars of physics, grows sharpest at singularities. Within a black hole's center, Einstein's equations predict infinite curvature. At the birth of the universe, they predict a singularity of density without bound. In both cases, space-time itself collapses. Yet perhaps the singularities are not real, but warnings. Signals that space-time is not fundamental, but emergent, dissolving at the ocean's surface into a deeper, undiscovered substrate. Hints of this possibility come from entanglement. Quantum mechanics teaches that particles can share states across distance, bound by correlations beyond spacetime's geometry. Some physicists now believe that spacetime itself may arise from these entanglement patterns, that geometry is woven from quantum information. If so, then the ocean beneath spacetime is not made of particles or waves, but of relations, of invisible threads of information knitting the cosmos together. The holographic principle sharpens this vision. In certain theories, all of spacetime and its contents can be described by a quantum field defined on a lower dimensional boundary. Like a hologram, the three-dimensional world may be a projection from a deeper surface. If true, then the forgotten ocean is not beneath spacetime in a physical sense, but beneath it conceptually, an invisible ledger of information from which geometry emerges. Even anomalies in the cosmic microwave background seem to hint at strangeness. The axis of evil, a puzzling alignment in temperature fluctuations across vast regions of sky, resists easy explanation. Low-power anomalies at large scales, hemispherical asymmetry, subtle but persistent. Could these be statistical accidents? Or are they fingerprints of processes beyond the horizon? Scars left by collisions between bubble universes, or echoes from a deeper oceanic turbulence. Inflation itself, invoked to explain uniformity and structure, raises its own enigmas. If inflation occurred once, why not eternally? Some models suggest that while inflation ended in our region, it continues elsewhere, spawning bubble universes in an infinite multiverse. Each universe with its own constants, its own geometry, its own surface waves upon the same hidden sea. If so, then our cosmos is not unique, but one ripple among countless others, forever separated, unreachable. Yet connected by the ocean beneath spetamy, dark energy intensifies the strangeness. Its pressure ensures that regions beyond a certain distance are lost forever. Galaxies once visible slip across a cosmic horizon, carried away faster than light by expansion. Even with perfect telescopes, their light will never return. The observable universe is shrinking in time, even as it expands in space. In the far future, only the nearest galaxies will remain visible. The cosmic microwave background itself will fade into undetectability. Cosmology, as practiced today, will become impossible. This temporal horizon reframes the forgotten ocean not only as a mystery of physics, but as an existential window. Humanity lives in a privileged epic debrief, span when the universe is transparent, when the afterglow of creation is visible, when galaxies still populate the night. The ocean shows itself now, but not forever. In time, it will withdraw into silence. Such realizations deepen not only the scientific mystery, but the philosophical unease. If space-time is emergent, if singularities are warnings, if horizons are rays, knowledge, then what is the ultimate nature of reality? Are the equations of physics glimpses of truth, or only surface maps of deeper currents? And if the ocean beneath space-time is built of information, what then is the role of consciousness, itself bound to the processing of information? the escalation of mystery transforms physics into something more. No longer the pursuit of equations alone, but a confrontation with limits, with horizons of knowledge. The ocean beneath space-time refuses to be fully charted. The deeper one dives, the more it recedes, suggesting not a bottom, but an infinite depth. And yet, the pursuit continues. For the escalation of mystery is not paralysis, but invitation. Every paradox, dark energy, black hole, evaporation, emergent geometries a doorway. The forgotten ocean conceals, but also promises. It withholds, but also beckons. The story of science is no longer about emptiness filled, but about nothingness. As foundation, a void that is not void, an ocean that underlies all shores. The escalation is complete. The mystery has grown from anomaly to abyss. The forgotten ocean beneath space-time is not simply a feature of physics. It is the horizon of understanding itself. The escalation of mystery left science at a precipice. Space-time, once considered the ultimate stage, now appeared as a fragile surface. Beneath it, the forgotten ocean surged with hidden depths. But what was this ocean? Was it the quantum vacuum, dark energy, information, or something beyond imagination? Here, theories unfurl like maps of an uncharted sea, some elegant, others terrifying, all incomplete. The first and most grounded theory is that the ocean beneath space-time is the quantum vacuum itself. In quantum field theory, every field electromagnetic. Higgs, gluon vibrates even when stripped of particles. Virtual excitations, ceaseless fluctuations, churn within the vacuum. This restless energy, the so-called zero-point energy, may be the hidden source of dark energy. In this picture, the universe's acceleration is not driven by exotic physics, but by the quiet push of the vacuum itself. Yet the calculation does not fit. The numbers overshoot by an impossible margin. If this theory is right, why is the ocean so calm when equations predict a storm? Inflationary theory offers another vision. According to Alan Guth, Andre Linde, and others, a scalar field once dominated the universe, a kind of false vacuum. For a brief moment, this field's energy drove expansion faster than light, smoothing irregularities, seeding galaxies. If true, then the ocean beneath space-time is not passive but generative. It is the very engine of creation. Yet inflation is a ghost. The field that drove it remains unseen. Its traces may linger in the cosmic microwave background, in subtle polarization patterns or primordial gravitational waves. But until such signals are found, inflation remains both elegant and elusive, a map without compass. Quantum gravity provides yet another lens. Both string theory and loop quantum gravity suggest that space-time is not continuous, but discrete, woven from indivisible quanta. If relativity paints space-time as a smooth sea, these models suggest it is more like foam, granular, bubbling at the smallest scales. In loop quantum gravity, space-time emerges from spin networks, mathematical knots of geometry itself. In string theory, space-time arises from the vibrations of minuscule strings and the folding of hidden dimensions. In either case, the ocean beneath space-time may be structured, not fluid, a lattice of existence too fine for current experiments to resolve. The holographic principle transforms the question altogether. Proposed by Gerard T., hoofed and expanded by Juan Maldacena, it suggests that the universe may be a projection, that everything we perceive in 3 dimensions, including space-time itself, is encoded on a distant boundary in 2 dimensions. The ocean beneath space-time in this view, is not physical substance, but information. Geometry is an illusion, like a hologram rising from a flat sheet of light. If so, then the forgotten ocean is not matter or energy at all, but bits of encoded data, the deepest language of reality. Entanglement offers a related speculation. Studies of quantum information suggest that spacetime geometry itself may emerge from webs of entanglement. In tensor networks, mathematical structures mimic the curvature of space simply by arranging quantum connections. Reality, in this interpretation, is not built from particles, but from relationships. Entanglement is the glue, and spacetime the tapestry it weaves. The forgotten ocean is then a sea of correlations, invisible yet omnipresent, giving rise to the very concept of here and there. Other theories venture into more unsettling territory. False vacuum decay imagines our universe as metastabler, bubble of higher energy vacuum floating in a larger sea. If the vacuum were ever to collapse to a lower state, it would trigger a bubble of new physics expanding at light speed, erasing all known structures. This is no fantasy. Calculations of the Higgs field's parameters suggest metastability is possible. If so, then the forgotten ocean is precarious, its tides shifting beneath us. Its stillness an illusion hiding catastrophic potential. The multiverse emerges naturally from inflationary models. If inflation occurs eternally in some regions, new universes may bud endlessly, each with its own constants and geometry. In this speculation, the forgotten ocean is not confined to our cosmos, but extends infinitely, spawning universes as waves spawn droplets. Our spacetime, then, is just one ripple among an uncountable infinity. Though unobservable, the multiverse lingers as a haunting possibility that the ocean beneath spacetime is infinite, and that our universe is not central, but incidental. Roger Penrose has offered yet another bold vision, conformal cyclic cosmology. In this model, the end of one universe cold, expanded, emptied of matter, becomes the beginning of the next. Radiation, stretched across eternity, becomes indistinguishable from the hot, dense state of a new Big Bang. If true, the forgotten ocean is not only beneath spacetime but beyond it, cycling endlessly through eons. Penrose even suggested that concentric circles in the cosmic microwave background may be evidence of events from a previous universe. Though controversial, such claims invite profound reflection. Perhaps the ocean has no beginning or end, but only cycles. Each of these theories pushes human imagination toward the brink. Yet none resolves the paradox fully. The cosmological constant problem remains unsolved. The unification of relativity and quantum mechanics remains incomplete. Every speculation reveals brilliance, but also fragility maps drawn on shifting currents. What unites them is a recognition that space-time may not be fundamental, whether through quantum foam, entanglement webs, holographic encoding, or inflationary fields. Space-time itself appears emergent. The ocean beneath is deeper than geometry, deeper than light, deeper than cause and effect. Speculation reaches even further into philosophy. If mathematics encodes the ocean beneath space-time, perhaps physical law is only an approximation of deeper logic. If information weaves reality, perhaps consciousness, so on information processes, not incidental, but resonant with the universe's foundations. Such ideas are untested, but they haunt the edges of discourse, where science and philosophy intertwine. The ocean beneath space-time, then, is not a singular idea, but a spectrum of possibilities. a vacuum alive with fields, a lattice of quantum foam, a hologram projected from unseen boundaries, a multiverse of infinite ripples, a cycle of universes without beginning or end. And yet, amid this diversity, a single theme resounds: space-time is not the bottom. The surface is fragile, and beneath it lies an order we do not yet comprehend. Theories and speculations are not answers, but lighthouses in fog. They do not pierce the ocean, but they illuminate its restless surface, suggesting the shapes of what may lie beneath. And though the sea remains unseen, its waves move through every star, every atom, every breath. The forgotten ocean whispers through acceleration, through radiation, through entanglement. And the more science listens, the more it realizes. The ocean is not forgotten at all. It is the silent foundation of everything that is. The forgotten ocean beneath space-time is invisible to the eye, untouchable to the hand. Yet science is not content with mystery alone. Across deserts and mountaintops, deep beneath ice, and high beyond the atmosphere, humanity builds instruments to probe this hidden sea. Each tool is not only an extension of sight, but a vessel launched into the unknown, searching for signs of currents beneath the cosmic surface. The Large Hadron Collider at CERN is one such vessel, a 27-kilometer ring buried under the fields of Switzerland and France. It smashes protons together at near-light speeds, recreating energy's last present moments after the Big Bang. Here, in flashes of subatomic debris, the Higgs boson was discovered. In 2012, the particle that confirmed the Higgs field, an invisible ocean giving mass to matter. Yet the discovery was not the end, but a beginning. Physicists now probe the Higgs with exquisite precision, asking whether the vacuum itself is stable. If the field wavers, even slightly, it could hint that our universe floats precariously on a metastable sea, liable to collapse into a lower state. Beyond CERN, future colliders are planned. The Future Circular Collider in Europe, the International Linear Collider in Japan. Each promises to dive deeper into the vacuum, seeking whispers of supersymmetry, dark sectors, or exotic fields. If discovered, these would be glimpses of the ocean's undercurrents, invisible layers beneath space-time's calm surface. But colliders are not alone in this quest. Space itself has become the greatest observatory, a stage for instruments that turn silence into revelation. The Hubble Space Telescope offered humanity its first deep glimpses of galaxies billions of years old. The James Webb Space Telescope extends this reach into the infrared, peering through dust to the cosmic dawn when the first stars ignited. Yet Webb is more than a stargazer. It is a historian of time, gathering light shaped by the ocean of quantum fluctuations during inflation. Its measurements of galaxy formation test cosmology at the edge of certainty, hinting at whether our theories truly capture the ocean's depth. Cosmology missions focus even closer on the forgotten ocean signature. Euclid, launched by the European Space Agency, maps the large-scale structure of galaxies with extraordinary precision, seeking to unravel dark energy's role in accelerating cosmic expansion. NASA's Nancy Grace Roman Space Telescope will soon join this endeavor, probing the geometry of space-time itself by observing distant supernova and the bending of light around galaxies. These missions do not merely catalogue stars. They measure the push of the ocean beneath space-time as it swells the universe outward. Yet the most profound probes are aimed not at stars, but at relics from the earliest seconds. Experiments such as CMB's 4 and Light Bayard will scan the cosmic microwave background with unmatched sensitivity, searching for polarization patterns, subtle twists of light that could reveal primordial gravitational waves. These waves would be echoes from inflation, vibrations of the ocean beneath spacetime frozen into radiation itself. To detect them would be to hear the forgotten oceans roar at the birth of time. Gravitational wave observatories extend this reach even further. In 2015, LIGO detected ripples in spacetime from colliding black holes, proving Einstein's century-old prediction. Now, with Virgo in Europe and Kagra in Japan, the network grows. These detectors listen to cosmic cataclysms, their lasers stretched and squeezed by waves passing through Earth. Yet the ambition does not stop here. The planned laser interferometer space antenna LISA will orbit the Sun, spanning millions of kilometers. Sensitive to longer wavelengths, it may detect waves from the earliest epochs, perhaps even relics of inflation. Such a discovery would be nothing less than the ocean's signature, carried across 13.8 billion years. Beneath Earth's surface, other instruments probe the ocean in silence. In Antarctica, the Ice Cube Neutrino Observatory transforms a cubic kilometer of ice into a detector, catching ghostly particles born in violent astrophysical events. Among these neutrinos may be relics from the first second of the universe, messengers from beneath the veil of spacetime. Similarly, Japan's Super Kamiokande and future Hyper Kamiokande search for neutrinos from supernova, the Sun, and perhaps from the cosmos's infancy. If detected, relic neutrinos would open a new window on the forgotten ocean. Older than light itself, even more delicate experiments test the vacuum directly. Casimir effect measurements, once crude demonstrations of metal plates drawn together, are now refined into precision science. Sensitive instruments detect tiny forces exerted by vacuum fluctuations, probing the restless sea at scales invisible to sight. Quantum simulators laboratories using ultracold atoms and Bose-Einstein condensates mimic black hole horizons and Hawking radiation. These tabletop experiments are not mere analogies. They allow physicists to test how the ocean beneath spacetime might behave under extreme conditions, impossible to recreate otherwise. Supercomputers join the fleet of tools, simulating the quantum seas where experiment cannot yet reach. Lattice quantum chromodynamics models vacuum fields, while simulations of holographic spacetimes test whether entanglement alone can weave geometry. These digital explorations are maps of possibility, suggesting how spacetime may emerge from quantum depths. The Square Kilometre Array, under construction across South Africa and Australia, will soon become the largest radio observatory ever built. With its sensitivity, it will map neutral hydrogen across cosmic time, tracing how galaxies and cosmic structure formed. In doing so, it will reveal how quantum ripples in the forgotten ocean became the vast cosmic web. All these tools, from colliders to satellites, from icebound neutrino detectors to radio arrays, converge on a single question: what lies beneath spacetime? They do not answer directly, for the ocean resists exposure, but each measures its surface, listening for echoes, shadows, and distortions that betray the depths. Yet there is urgency in this endeavor. The universe itself is changing. Dark energy ensures that galaxies will drift beyond reach. The cosmic microwave background will fade, and the evidence of the ocean will one day vanish. The instruments of today are not just machines of curiosity. They are guardians of memory. preserving knowledge before the cosmos erases its own story. In the end, these scientific tools are more than machines. They are extensions of the human spirit, fragile yet relentless. Each collider, each telescope, each detector is a net cast into the deep, drawing fragments of truth from waters we cannot see. They are humanity's way of touching the ocean beneath space-time, even if only through ripples and reflections. For now, the tools continue their work. Lasers whisper across vacuum chambers. Antennas listen to the hum of hydrogen. Detectors wait in darkness for a single neutrino to pass. In these quiet experiments, humanity leans closer to the forgotten ocean, hearing its faint pulse, feeling its hidden tides. And though the ocean may never reveal its full depth, science persists an unending voyage across a sea it cannot escape and cannot yet comprehend. Beneath every equation, beneath every telescope's image, beneath the whisper of particles and the roar of galaxies, lies a silence that is not emptiness, but depth of forgotten ocean beneath space-time. For centuries, humanity believed the cosmos to be a solid clockwork, a stage set with stars and planets moving in orderly rhythm. Then came relativity, teaching that space-time is no stage at all, but a living fabric, curved and elastic. Quantum mechanics went further, revealing that even emptiness trembles with invisible storms. What was once thought to be void is now seen as a reservoir, an inexhaustible sea of possibility. And yet, as the discoveries accumulated, so too did the questions. Why does the ocean exist at all? What stirs its tides? Is space-time the true foundation, or only a mirage above deeper waters? Every instrument points toward the same haunting realization. The familiar world is not fundamental. Distance, time, solidity all may be emergent, like foam on the crest of waves. If so, the ocean is not merely beneath space-time, it is beneath perception itself. Consider the paradox. The vacuum appears empty, yet it shapes the expansion of the cosmos. Black holes, once thought silent, sing through hawking radiation songs, born of the vacuum's fluctuations. Even the mass of matter is not intrinsic, but lent to particles by fields that pervade space unseen. Existence itself seems to float on something we cannot touch, yet cannot escape. This is the unsettling beauty of the forgotten ocean. It is both everywhere and nowhere. It hides in silence, but its fingerprints shape galaxies, atoms, and minds. Philosophers once asked whether nothingness could exist. Today, physics answers with contradiction. Nothingness not only exists, it is restless, fertile, creative. It births particles, drives expansion, fuels the stars. The forgotten ocean is the canvas upon which the cosmos paints itself, the stage. That is no stage, the silence that generates song. But if the ocean is real, what does it mean for humanity? For centuries, humans have stood at the shore of seas they could not cross, staring toward horizons they could not reach. Now, the greatest sea of all lies beneath their feet, invisible but infinite. Science confronts its own horizon here. Equations strain, diverge, collapse. Relativity and quantum mechanics, the twin pillars of modern physics, clash in their attempts to describe the ocean's depth. Each offers glimpses, but neither reveals the full truth. The forgotten ocean is not only a frontier of science, it is a frontier of thought itself. Perhaps this is its deepest lesson, that knowledge is never complete, that certainty dissolves at the edges. The ocean reminds us that reality may be layered beyond comprehension, that truth is not a final equation, but an unfolding tide, and yet, in this incompleteness, there is meaning. Humanity is not diminished by the ocean's mystery. It is elevated. To know that reality is deeper than perception, wider than imagination, is to glimpse the grandeur of existence itself. In the far future, when galaxies drift beyond sight, when the cosmic microwave background fades into silence, the ocean will remain. Invisible, immeasurable, yet shaping all that endures. Civilizations may rise and fall, stars may ignite and die, but beneath every change, the sea will continue to move. What then is humanity's place? Fragile beings, born on a small planet, daring to map an ocean they cannot see. Their instruments are frail, their equations incomplete, yet their questions endure. To look upward, to imagine downward, to wonder what lies beneath, that is the essence of being human in every observatory, in every collider, in every quiet detector buried in ice or orbiting the stars. Humanity extends its reach into the unseen. Each is a lighthouse built upon the shore of the forgotten ocean. Each sends a beam of curiosity into the dark, knowing that the waves may never be fully charted. Perhaps space-time itself is not ultimate. Perhaps the ocean is not physical, but informational, a vast lattice of entanglement from which geometry arises. If so, then reality is not matter, nor energy, nor space, nor time. It is relationship, pattern, connection. The universe, then, is less a machine and more a poem, written not in stone, but in waves. This vision is at once humbling and profound, for it suggests that the deepest truths may never be captured by measurement alone. They may lie beyond mathematics, beyond physics, in realms where imagination and philosophy must sail together. The forgotten ocean beneath space-time is not merely a scientific mystery. It is a mirror reflecting humanity's longing to know, to cross the horizon of ignorance. It tells us that the universe is not static, not final, but endlessly layered, endlessly deep. And perhaps that is the greatest gift of the ocean. Not answers, but questions. Not certainty, but wonder. The story ends as it began, with silence. The silence of a universe drifting on unseen waters. The silence of fields that hum beneath perception. The silence of a sea that has always been here and may always remain. Humanity stands upon its surface, listening. Equations stretch like fragile rafts into the dark. Instruments cast nets into the invisible tide. Minds reach downward, imagining what cannot be seen. And though the ocean may never be fully known, it is already part of us. Every atom in every body, every photon that strikes every eye, every thought that drifts through every mind is shaped by it. We are not above the ocean, nor beside it, we are within it. The forgotten ocean beneath space-time is not only the foundation of the cosmos, it is the foundation of being itself. Final vision, the universe as a fragile vessel, carried across eternity by a sea without shore, and humanity's more finite, yet awake sailing upon its waves, daring to dream of the depths.